2-year-old at home, I always have to write something.
Well, we're still in the right book, so that's a good thing. So, probability. Is probability relatively important to us? Well, only if we go to the casino, right? If we're at the casino and we're throwing away our money, if we knew anything about probability at all, would we be at the casino? And the answer is no, we wouldn't, because the odds are against you. You will, in fact, lose. And so that's just the way it is. You have days like that. So we do experiments, and we count things to see what the probability is. You're playing some game and you're rolling a 6-sided die. You have some idea how often you're going to get a 1, right? You know, pretty much. And if you didn't, you'd roll the die several times. If you're at somebody else's house, you want to make sure the die are fair, so you roll them several times before you play the game. Events can happen. So there's a certain probability we're going to have class next Thursday, right? And there's a certain probability Jody isn't going to be here, right? So the probability of having the class is pretty high, but I could drop dead, you know, right? That's a possibility, and we wouldn't have the class. So maybe it's only 99%. But Jody won't be here. She's got a plane to catch, and she'll be on that plane. And so it's 100% probability of that, events. There's some basic relationships we have to consider. We have conditional probability. Okay, so I'm going to flip this coin. If it's a head, then I'm going to flip this coin over here. But if I flip this coin and it's a tail, then I'm not going to flip this coin over here. So it's a conditional thing. Something has to happen before something else. In Bayes' theorem, your guess is as good as mine. When we get there, we'll figure that out. So there's certain things in life that are uncertain. So we buy car insurance. Why? Well, because we have to, right? We buy health insurance. Why? Well, now we have to. We didn't used to. We buy life insurance. Why? Well, because there's uncertainties in the world. It's probably extremely unlikely that some manned gunman's going to walk through that door and start shooting us, right? But we should be ready in case he does, right? So we should have a plan. So what's our plan?
I'm jumping out the window.
Yeah, that might not work. So my plan is he doesn't reload. Okay, so that's the plan. So if he wants to come in here and shoot us up, that's fine. But no matter how much badly we're bleeding, he doesn't reload. And so that's the plan. Yeah, so the plan's terrible. Okay. Well, you have uncertainties in life, you have a plan. The plan during the middle of the Cold War was, in order for the penetrating bombers to penetrate, the submarine force had to put 750 nuclear weapons on the anti-aircraft assets of the Soviet Union. Really dumb plan. I mean, I could have come up with a better plan than that. But managers like to base their decisions on some analysis of the uncertainty. So I'm making toothpicks. Am I going to sell some toothpicks? No. Well, who uses toothpicks? People that want to have cheese, right? Cut up cheese and have toothpicks in them. So I'm gonna use some every year. I'm gonna use some toothpicks. I can make some. I don't want to make too many, then the price drops. Chances of sales may increase or decrease depending on the price. So every 6 months for the last 10 years, somebody's been at my door trying to sell me replacement windows, and the price isn't right yet, so they go away. There's a likelihood that something will happen, and there's odds that a new investment will be profitable. I was listening to some radio show going back and forth, and in the last 4 years, the stock market's up 60%. So if you have a stock market portfolio that went down, something's wrong. That shouldn't have happened. That's against the odds. Probability, numerical measure of the likelihood of an event occurring. So I've been here for 17 years at Iowa Western. In that amount of time, I've missed maybe 3 days because of sickness. So the probability of me being sick and missing class, next class period, is slim and none. And because of the distance between you guys and me, I could be up here all sick and you wouldn't even know it, right? Well, I'm sick anyway. You already know that. Right? I'm sick in the head for doing this, right? So probability values go from 0 to 1. So if there's a quiz question or a test question that says the probability is 2 of something, then we cross that out. It can't be that. So probability is, it's a 1, it's going to happen. It's 0, it's not going to happen. So the sun is going to supernova. Well, that would be a 1. In our lifetime, that would be a 0. But sometime 3 billion years from now, the sun will run out of helium and go into a phase where it will supernova, and that'll be a catastrophic event, and expand to greater than the orbit of the Earth, and will be part of the sun at that point. Those of us that are left. Anybody going to be here 3 billion years from now?
Do what?
Huh? I just wondered what the probability of you being here 3 billion years from now was. Was that 0 or a 1 or?
0.
Yeah, that might be a 1. Think about the advances in medical technology over the past 100 years or so, and then think about what would happen if we suddenly didn't get ill and suddenly didn't age and suddenly stayed here for a long time because of the medical technology changes. So there is a slight probability that we're going to be here for a long time. Now, that would cause all kinds of other social, economic stresses and strains, because the whole economy is based on us dying off before we're 100 years old, right? And so that would be, anyway, a probability event near 0 indicates it's not very likely. Probability near 1, it's probably going to happen. So will somebody win the Super Bowl this year? Yes, it's not going to end in a tie. It's very likely. Will it be the 49ers? Well, we'll wait until the game's over, find out, right? Right now it's 50-50. Either one of them could win. If either of them had a big lead at halftime, then it might shift a little bit. Do you watch the poker tournaments on ESPN at all? So, the guy's sitting there with 8 high, and the other guy's got 3 of a kind, and the probabilities are way against him, and then his straight comes through, and now the guy that was 8 high now has a straight and beats the 3 of a kind. Yeah. So those are all probability type things that those guys are paying attention to. So here we go. Probability 0 to 1. Equal opportunity there. If I flip a coin, I have an equal opportunity of heads and tails, right? No. Because the coin is going to be weighted one way or the other. You're going to be more heads or you're going to be more tails, but you're never going to be 50%. You could flip it 1,000 times. You're still going to have more one than the other. And there's always the possibility that it's going to land on its edge, right? So there's 3 possibilities, or there's 4 possibilities, right? Maybe 5. So heads, tails, it could land on its edge. It could stay up in the air and not come down. So that's 4 possibilities. 5 if you throw in it enters a new dimension and it disappears altogether. Yeah, Well, some of those aren't very likely, right? Yeah, not very likely. Statistical experiments. So here I'm going to go, and I'm going to go and It's different. It's a little bit more than physical things. So physical things, I'm flipping a coin. I'm talking about a tree growing. I do an experiment now. Okay, we're back. Back in operation. Statistical things, determine outcomes. Even though the experiment can't be repeated exactly the same way, the outcomes may occur that way. So you're playing some game and you're always losing. You play it the next time, what's going to happen? You're going to lose, right? So you're playing, unless you're playing something good like Skippo. So statistical things sometimes called random experiments. So we have some experiment, and in that experiment we have a generated set of outcomes. We know what they are. We have a sample space that we're sampling from. So I've got red. Oh, there we go. We have right there. We have red and yellow and brown and black M&Ms.
No.
And no black.
That's Skittles.
There's Skittles. Okay,
Red,
Skittles.
yellow, green,
So you close your
purple,
eyes and you take one out. There's some probability of getting a color. But we know that the colors that are in the bag are the only colors I can pull out. An experimental outcome is a sample point. I'm sure that that's on the quiz I'm passing out at the end of the class period. So tossing a coin, inspecting a part. If I'm building a car, I conduct a sales call. I roll the dice. I play a football game. Unless you're playing against Iowa Western, then you're going to lose. Right. Now our basketball team has lost a game already, so I think we're 20-1 right now for the season. So, but the football team, they didn't. How can you have a winning football team at a community college? How is that possible? You know, it just boggles the mind. But we have win, lose, and tie. Can we tie a football game these days? I guess we can.
As long as it's not a playoff.
Yeah, for as long as, yeah, I guess we can. Purchase or no sale, defective, not effective, heads and tails. I would add it's on its edge, but that's just me. Bradley Investments, they have two stocks, in oil and in mining. Now, anybody that knows anything about stocks is you should not have two of them, right? What's the minimum number of stocks you should have? Anybody have any idea? You should have at least 10. Now, if you have some mutual fund, the mutual fund has several thousand different stocks in it, so that's not an issue. But if you shouldn't, in any individual stock, you shouldn't have any more than about 4% of your total worth in a particular stock. Because at any moment, that stock could go to nothing, and you wouldn't want it to be too high. All right, so here's the gains and loss for the last 3 months in thousands of dollars. So Merkle goes up 10, goes up 15, and then down 20. So it looks like a loss. And the mining guy is up 8 and then down 2. All right. I don't see why that made any sense, but so we have a counting rule for a multiple step experiment. If an experiment consists of a sequence of more than one step in which there's n possibilities, then the probability of having the outcome be exactly n1, n2, we have to multiply those together. Okay, so I'm going to flip a coin 10 times. What's the probability of me having a head, tail, head, tail, head, head, tail, head, tail? Was that 10? Yeah, if that were 10, then the probability of each of those events would be 50%, 1/2. So 1/2 times 1/2 times 1/2 times 1/2 times 1/2. That'd be 1/2 to the 10th power. I could put it in my calculator and I could come up with the probability of me getting exactly that sequence of heads and tails. Do I have a coin? Oh, I have a coin. Okay, well, so we'll try it. No, won't try it. But I'm multiplying the probability of each step together to get an outcome. Oh, good. Now we're going to do a graphical representation, a tree diagram. All right. So, two-step experiment involving two stocks and set of outcomes. And so we could gain 5 even or be there, or we could go down 20, or we could gain or lose 8. Oh, isn't this special? So when we get done, our portfolio could be in any one of 8 different places. Am I on the moon yet? No. So obviously there's something wrong there. So, but anyway, that's what I was saying. So I could, given that I start there, stage 1 is what Merkel's doing, stage 2 is what Collins Mining's doing. They could both be up and I could be very high, or they could both be down low and I could be very low, or any place in the middle. So then our experimental outcomes, I could gain, I have to push my button? Yeah, I got to push my button. So I could gain or lose lots of money. Now, it shouldn't do that, right? It shouldn't say lose 2,000. The 2,000 should be in brackets to indicate that it's a loss. This is not really a business class, so we'll let the author get away with that. But he should have put these in brackets to indicate that they're losses. He shouldn't use the word lose there. Very demeaning. Number of combination of n objects taken n at a time. So a second useful counting example. Use count experimental outcomes. I have a bowl of apples, and there's green ones and red ones, and I take out 2 of them. Okay, so what's the chance of having 2 red ones or 2 green ones? So the outcome would be n objects taken little n at a time. Now, if you look in your calculator, you probably have a button that says something. Let me get out of here. You probably have a button that says NCR. You have a button that looks like that someplace on your calculator? It's probably right next to the button that says NPR. It looks something like that. This is the combination of n things taken r at a time on your calculator. So if I put in 25, well, I have to turn myself on. 25, and I need C and R 2. So the combination of 25 things taken 2 at a time is 300. So 25 NCR 2 ends up giving me 200. All right, back to our transparencies. The combination of n things taken n at a time would be n factorial divided by little n factorial minus n factorial. Okay, so let's see if I can remember that. n factorial, little n factorial, n minus n factorial. All right, so 25 factorial divided by 2 factorial times 23 factorial. And that's supposed to be 200? Find that hard to believe. Okay, 25 factorial divided by, you find the factorial key on your calculator?
Which one's that? The exclamation point?
Yeah, the exclamation point. And I get 300 again. This was 300 the first time, in case anybody was wondering. I don't know how I read it as 200. So you can go 25 factorial divided by 2 factorial times 32 factorial and get 300. Or you can put in your calculator 25 things taken 2 at a time and get 300. Okay, so what's the chances of you remembering that? Poor. How about this on your calculator? You're going to remember where that is? Probably. Okay. Do I need to... Okay. Back to...
5,
yes.
5 factorial should be 120, not
Yeah.
15.
5 double factorial would be 15. I agree. But 5 factorial would in fact be 120. I agree.
We never actually use double factorial.
In this class?
Yeah.
Never. Okay, so it's considered a historical thing, something that you'd use if you're teaching your third graders math. You'd talk about it. So I've seen the notation in my differential equation book where it made a lot of sense to use it there, but I haven't seen it anywhere else. Okay. So that's combinations taken one at a time. We also put a capital N over N with brackets to do the same thing. Combination of n things taken n at a time. There's my 0 factorial is 1. Permutations, this time in a combination, it doesn't matter what order you're in. Well, a combination matters the order. The permutation doesn't matter the order. So this is n objects, but the selection of how they are is not important. So in the combination, if I'm supposed to see a red, blue, red, then I have to have a red, blue, red. In a permutation, it could be red, blue, red, or it could be red, red, blue, or it could be blue, red, red. That'd be the same thing. So my permutation is going to be n factorial divided by n minus n factorial. And again, on your calculator, you have that button that does permutation. So we'll end the slideshow for a moment. And so if I have 25 things taken 2 at a time, and now the order doesn't matter what 2 of those are. I can take my calculator, go 25, so I'm going on 25 NPR key 2. And I end up with 600. So I end up with, so that would be a permutation. So if I want a permutation, I use my P key, and if I want a combination, I use my C key, and if I can't use either, then I have to use the factorial key, and remember the formula is, where's the formula? There it is. N factorial divided by n minus 1 factorial. N minus n factorial. Capital N minus little n. Okay, all right with that? Not really? As long as I have this on the board, would you be able to do it in your calculator, maybe?
So then what's the difference between that one and the C one?
The C, the order matters. The P, the order doesn't matter.
Like the 25 and the 2?
Yeah. So selecting a set of n things where the order of the order of selection is important. So permutation, the order matters. Combination, it doesn't matter. And that's why there are more of them. If the order is going to matter, I need to have more possibilities of things happening. So
combination order doesn't matter.
Doesn't matter. Combination order does matter.
Combination order does matter?
No. Permutation does. Selection order important. No. Does not. No, there's no good way to memorize that.
C does?
C does not. P does. Yeah. So when I'm writing the equation on the board, have me add whether the selection is important or not. Okay, number of. Okay, we just did that. Assigning probabilities. Some basic requirements for assigning a probability. All right. The probability assigned has to be between 0 and 1. Can't be outside that. I can't have a -3 as my probability. That won't work. So the probability of some event occurring is between 0 and 1. E is the event, I is the experimental outcome of that particular time that I do it. The sum of the probabilities for experiment must also equal 1. So I'm rolling a die. I have a 1/6 chance of getting a 1. I get a 1/6 chance of getting a 2. I have a 1/6 chance of getting a 3. I got a 1/6 chance getting a 4, a 1/6 chance getting a 5, a 1/6 chance getting a 6. When I add up 6 1/6s, I end up with 1. The sum of the probabilities of the experimental outcomes have to be 1. Where n is the number of the possible outcomes. Sign base probably based on the assumption of equally likely outcomes. Okay, so when I'm rolling a die, it's a 1 would be an equally likely outcome. Now I was just watching Guys and Dolls 2 nights ago, and Big Julie came in with a set of die where he had taken the spots off, but he still remembered where they were. And when he rolled the die, he would win most of the time because he remembered what the spots were. Okay, so those would not be fair die. Normally, you'd have to roll your dice 1,000 times to figure out how fair they are, and they're probably not. You're probably going to get some number more often than another one, just because of the manufacturing process. Relative frequency method, assign probability based on experimental data. So, and subjective method, guess. Okay, what's the probability of the budget of the United States being balanced next year? Well, 0. Maybe it's 0. Maybe it's not, but it'd be a subjective thing. Okay, so I'm going to roll a die. 6 possible outcomes, 1 out of 6. I could have a 12-sided die, right? So I could have a 12-sided die that only has numbers 1 through 4 on it. I could do that. Experimental, we roll the die to figure out what the chances are. Locus tool rental. I like to assign probabilities that the number of car polishes it rents each day. All right. So number of polish of Porsche. What is that? Polishers?
Yeah, polishers.
Polishers rented? Oh, right. So it's renting tools and it's renting polishers. Okay, so on 4 days during the month it didn't rent any, but 2 days during the month it rented 18 times during the month it rented 2. Okay, so we have some probability of renting a polisher. So I don't want any more than 4 in my inventory, right? And so we divide the numbers and we end up with the probabilities. And when we add the probabilities together, we get 1. Okay, so we have a total of 40 days. 4 days out of the 40, or 10% of the time, I don't rent any. Right, well, as long as the data set's that small, I guess I can handle that. Subjective method. Economic conditions of a company, rapid change, assigning probability based on historical data, degree of brilliance. Well, if the boss thinks it's that way, that's clearly the way it is, right? Yeah. Best probability estimate can often be obtained through classical or relative approach. Okay. Analysis of the probability. Okay, so here we go. Probability of gains and losses. Okay, I look at that and I say, I'm not buying any of that stock. The event, a collection. Okay, so I have some event, which is a collection of data points. The probability of any event equal to the sum of the probability of the sample points. If we can identify the sample points, then that's good too. All right. Bradley's investment again. Okay, there's my sample points. I'm up, down, and then there's a probability of those particular points happening, and I calculate those probabilities, and they add up to 70%. Huh. Collins Mining being profitable. Profitability. And I get data points. So a 42% chance of the mining being profitable. I don't want to buy that guy. I like the other guy better, 70%. Basic relationships. All right. Complement of an event. So the event is A. The complement would be not A. So the event is I have a tail, I flipped a coin. The complement would be a head, not the tail. So I could have a complement of an event. The federal budget is going to be balanced this year. That's the event. Probability very small. The complement of that would be the federal budget's not going to be balanced. Very high. The union of two events. That means I need both events. The intersection of two events. Mutually exclusive events. Okay, so I'm driving home tonight and Todd's driving home tonight. what is the probability of I'm driving Todd's car and he's driving mine? Mutually exclusive, right? I'm going to be driving mine, he's going to be driving his. Mutually exclusive events. All right. Union, intersection, mutually exclusive, complement means that we can draw diagrams again, right? So union means I have two circles in a Venn diagram and there's something that they're both agree on. The whole and the union of those two. Intersection where they meet. Mutually exclusive, my two circles are away from each other. So now we're into doing Venn diagrams, and so we complement of an event, not A, not A. So A, complement of A. We also use A bar above the A would also mean complement of A. So here's an event A, there's our sample space, and not A would be every place except for where the event A is. And we call that since 6th grade a Venn diagram. Do we remember that since 6th grade?
Remember yesterday.
Yeah, it was just like yesterday. Yeah. Union of two events. A, union, B. U thing. Oh, went too fast. So, A, union, B. I got event A, and I got event B. Everything else, everything that's inside those two circles would be A, union B. Outside would be the complement of A, union B, not A, union B. So the event is Merkle probability and Collins profitability. The union of those two events would be both being profitable. So we have those events, and they have to both be profitable this time. 0.82. They don't have to both be profitable. It's a union, so if either one is, then it counts. When it's intersection, then they both have to be. Intersection of two events. A and B. Now we turn our U thing upside down, which means intersection AB. We have a Venn diagram, so I've got event A, I got event B, I got a sample space, the whole thing. A intersection B, the lens thing in the middle. And now we look at our profitability again. And the intersection of them being profitable comes out to 36%. Again, I don't want to be in these stocks. Addition law. I'm going to add something. The probability of A or B or both A and B occurring. So that's the issue is what's the probability of A or B or both occurring? And so we write the probability of A union B. So that's the probability of A plus the probability of B minus the probability of A intersection B. And that'll be so cool. I hope they give us a picture of that. So the probability of A union B, I know the probability of A, I know the probability of B, I can subtract the intersection, all I have to do is know what it is. So here we go. Profitability again. We know those profitabilities. We know everything there is to know. So the probability of A union B union C, so of both of them being probable, probability of one plus the probability of the other minus the intersection of the two. 0.82%, 82% going to be probable. All right, so we're going to remember that equation. Well, maybe for the rest of the day. Let's hope so. Mutually exclusive events. All right. Mutually exclusive. They have no sample points in common. So I got a die, and I want ones, and I want sixes. If I roll a die and I get a 1, can I have a 6? No. Mutually exclusive. Two events are mutually exclusive if one event occurs, the other one cannot. And now we have a sample space, so showing mutually exclusive events, they have no intersection. All right. Events A and B are mutually exclusive if their intersection, the probability of the intersection is 0. The addition law says that the probability of A union B is just the probability of A plus the probability of B, because the union is now, the intersection is 0. Probability of the intersection is 0. I don't have to write it down anymore. So I have a different addition law if my probabilities are mutually exclusive. Conditional probability. Okay. What if the instructor comes to class, is the class going to be held? There's a probability, right? But if the instructor didn't come to class, what's the probability of the class still being held? Conditional. The class being held is conditional upon the instructor showing up, right? In general, maybe. Okay. Probability of event given that another event is going to occur is called a conditional probability. And we got a line, so probability of A given B is denoted with a straight bar going up and down. I know you wondered what that was doing on your keyboard, the straight line going up and down. That's what it's there for. Conditional probability is computed as follows. The probability of A intersection B divided by the probability of B. Okay, so in order for A given B, they both had to happen, right? So that's how I'm going to compute it. And maybe I'll remember that. Conditional probabilities. Column is probable given that Merkle is profitable. Okay, so those are our what we know to be the case, and so we 0.514%, 51%. Why we have 4 significant digits there? We shouldn't. No, we don't have 4 significant digits. Multiplication law, okay, provides a way to compute the probability of the intersection of two events. Okay, law is written as problem. So A union B is the probability of B times the probability of A given B. And why I would do that, I don't know, but sounds like a lot of work. Okay, so now I'm gonna do that, and I come up with 0.36. All right, so that's fine. So I got a multiplication law. Joint probability table. All right, we're gonna have, so Merkle in Collins, profitable, not profitable. All right, so I can calculate and when Merkle is profitable, Collins either is or isn't. When Merkle isn't, Collins either is or isn't. And total probability is 1, so that works. And total probability the other way is 1, so that works. All right, independent events. Let me think. The radio station is playing a particular record right now, and we are in this class. And those would be independent events. We had no influence on the radio station. They had no influence on us. Two independent events are independent if given A happens, B happens, that's just a probability of A, or if B happens, A has happened, just a probability of B. Totally independent of each other. Multiplication laws for independent events. Two tests are independent. So union, the intersection of A, B, given that they're independent, is the probability of A times the probability of B. Are the events of the mining guy and the oil guy, are they independent of each other? So does the probability of M intersection C equal that? And we find that it does. It does not. So they appear not to be independent events. They're controlling each other somehow. Not independent. Mutually exclusive and independent. Do not be confused. Mutually exclusive with independent. Two events with zero probabilities cannot be both mutually exclusive and independent. Non-zero. If one mutually exclusive event is known to occur, the other cannot. Thus, the probability of the other event occurring is reduced to 0, and they are therefore dependent. Yeah, okay. Mutually exclusive. Okay, so if one occurs, the other can't. They are dependent upon each other. Okay. Two events that are mutually exclusive might not be independent. Whatever. And here is Bayes' theorem. Initial or prior possibilities. Okay, so I just rolled a 6, and I got the die back, and I'm going to roll again. Does it matter that I just roll a 6 when I roll the die another time? No, it doesn't. So that I had a 6 the last time doesn't make any difference. I still have one chance out of 6 to get it this time. Then from a sample special report or product test, you have information. A means of revising prior probabilities. Okay, so I have these prior probabilities of a baby aspirin stopping my heart attack. I have new information that says it'll also stop colon cancer, and so now I can go in and change those probabilities on this miracle drug aspirin that I'm taking. L&S Clothiers. So we have this shopping center will provide strong competition to the downtown. Okay, yes it will. Unless it runs out of money and folds first. the shopping center cannot be built unless a zoning change is approved. So A1, the town council approves a zoning change. A2, it doesn't. We have some subjective probability based on who's on the city council of 0.7 and 0.3 of those two events. Okay. The planning board has recommended against the zoning change. B denotes the event of the negative recommendation. Given that the negative recommendation has occurred, what are the chances of the town council doing the right thing? And past history, we have some indication of past history. So in the past, the probability of the guys doing something based on what the planner said, 0.2 and 0.9, okay? Hence we have some other things, and now we can up to, we're going to do a tree analysis, okay. And so given that the planning board has done something, we end up with the probabilities. Well, that's clear as mud. Is that clear as mud? Yeah, pretty much. Okay. Define the posterior probability of event A will occur, even though event P has already occurred. We apply the theorem. Oh yes, there. Memorize this equation. This looks very good here. So, yeah, especially have 30 or 40 events, right?
Wow.
Yeah, that. Remind me. Send me an email. Tell me not to put that on the next test. The planning board's recommendation not approve the zoning was revised prior to it being made. So I revised it. 0.34, and the planning board's recommendation is good news compared to that way, and okay, that's fine. Tabular approach, step 1. Prepare a column for the events and hope for the best. All right, so here we go. Probability. Do I have to hit it again? Yes, I do. Conditional probabilities. Step 2. Prepare a fourth column of the joint probabilities. Okay. Joint probabilities. And I'm going to multiply those two together, joint probabilities. Those two multiply together, joint probability. And I'm going to do it again. Step 3. Joint probabilities column 4, sum of the other two. All right. Compute the probabilities using the basic relationship of the condition. Probability of the intersection divided by the probability of B, okay? So there's the intersection, probability of B. And now we have more numbers. End of chapter 4, yay! Okay, now we got to do homework. And we might actually have enough time to do the homework, who knows? Now there seems to be a whole lot of equations we better remember, right? Well, at least the instructor, and probably need to buy a better calculator before the next test. Yeah, that might be it too. Okay, so do I need to get out my syllabus and figure out what problems I'm working, or?
I've got them right here.
You got them right there. Okay, now first problem is?
Number 5.
Okay, so we're in chapter 4, trying to find out where problem 5 is. Okay, I think I'm on page 158.
Yep.
Suppose an experiment has 5 equally likely outcomes. All right, so I got E1, E2, what does E stand for? Anybody know? E4. E is for event. Yeah, so that's event. All right, so that's what I got. Assign probabilities to each outcome and show that the requirements in equation 4-3 and 4-4 are satisfied. What method did you use? All right, so, okay, well, let's see, I'm going to do that. I'm going to just assign probabilities here. Point 1. Is that okay? Point 2. Point 3. Point 4. Point 1 again. Do they add up to 1? 4, 5, and 6. 5 and 6. Bummer. Bad choice. 3. There, is that better? So I made up numbers, made up probabilities. Okay, now we got to go to equation 4-3. And what do you say? So I see problem 4-3. So is 0 less than or equal to the probability of one of the examples, which is lesser than or equal to 1. So yes, the probability of each of those things is in fact less than between 0 and 1. So I did that right. And is the probability of event 1 plus the probability of event 2 plus the probability of event 3 plus the probability of event 4 plus the probability of event 5, is that equal to 1? Oh yes it is, and we made it equal to 1 before we started. Thank you very much. Okay, so did we do the problem right? No. What did we do wrong? Starting over on 5. E1, E2, E3, E4, E5. The events are equally likely, right? So this guy's got to be 0.2, he's got to be 0.2, he's got to be 0.2, he's got to be 0.2, he has to be 0.2. So equally likely would be 1, 2, 3, 4, 5, 1 out of 5, which would be 0.2. All right, now that we've done that, is 0 less than or equal to the probability of either any of the events less than or equal to 1? And the answer is yes, it is. Click. And is the probability of the summation of the events equal to 1? Click. Yes, it is. All right. But we weren't supposed to go and assign probabilities. We were supposed to make them equally likely. Okay, next problem.
11.
The National Occupation Protection Survey was conducted to provide probability-based data for motorcycle helmet use in the United States. The survey was conducted by sending observers at random to collect data on motorcycle helmet use. All right, blah, 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 blah. The data is as follows. Okay, so I see the data. Northeast, Midwest, Southwest, compliant, not compliant. 96 86, 92, 76, not compliant, 62, 43, 49, 16, 350, 170. I suppose I'm going to have to turn the page to see what I'm supposed to do with the data, right? I think I should do that. A. Use the sample data to compute an estimate of the probability that a motorcyclist wears the helmet. So, the probability of compliance, 350 divided by 170 plus 350. Probability of the event divided by the probability of all the outcomes. Okay, so take my calculator. 350 divided by, close parentheses, 170, open parentheses, plus 350. Boom. And we'll go with 0.67. Okay, so that's my A response. B. The probability that a motorcyclist wore a DOD compliant helmet 5 years ago was 0.48. And last year the probability was 0.63. Would the highway traffic safety be pleased with the most recent survey? This is just a yes or no. So I'm going to pick yes because they're more compliant. Or it could be no because the rate of increased compliance has gone down, right? So you could look at it either way. C. What is the probability of DOD compliant helmet used by region of the country? What region has the highest probability of compliance? All right, so we want the probability of compliance in the East, the probability of compliance in the Midwest, the probability of compliance in the South, and the probability of compliance in the West. That's what we're going to do. I got 96 divided by 96 plus 62. I got 86 divided by 86 plus 43. I got 92 divided by 92 plus 49. And I have 76 divided by 76 plus 16. Alright, so those are all the things we're going to do. God, shouldn't we? That would be a good idea too. Okay. So problem 11 is now done, and I think we agree with those answers. Okay, next problem.
17.
Okay, refer to table 4.2 and 4.3. Design stage 1, let's see. The design stage 1 will run over budget if it takes 4 months to complete. And then we're supposed to do that. Okay, so let's see if I can find table 4.2 and 4.1. Okay, I found table 4.2 and I found table 4, 3. Okay. A. The design stage 1, will run over budget if it takes 4 months to complete. List the sample points in the event the design stage is over budget. Number of days occurring, stage 1 design, completion of number of months. Sample points and sample point probabilities are there. List the sample points in the event the design stage is over budget. Okay, so if I go, if I'm greater than 4 months, then I'm over budget. And it looks like that's a 4, 6, a 4, 7, and a 4, 8. So that would be the sample months of being over budget. List the sample points in the event it's over budget. Okay. What is the probability that the design stage is over budget? Probability that we're over budget. Okay, so B, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 sample points. We're over budget for 3 of them, so that would be 1/3, 0.33. That would be the probability that we're over budget.
Where'd you get 3?
Well, 1, 2, 3
Oh.
cases were over budget. 1,
there's
2,
9.
3, 4, 5, 6, 7, 8, 9
Yeah.
total.
Understood the 9. Okay.
Yeah. Okay? Yeah, I didn't. I'm just making this up here. A, B, C. The construction stage, stage 2, will run over budget if it takes 8 months to complete. List the sample points to be over budget. Okay, so 8 is over budget at 2, 8, at 3, 8, and at 4, 8. Okay, so those are the sample times I'm over budget. What is the probability that the stage will be over, that the construction stage, probably 2 is over budget, so D would still be 3/9, which would still be 0.33. Echo. What is the probability that both stages are over budget? Both are over budget. Okay, so that's only one sample point, 4, 8. So for both to be over budget would be 1/9. 1 divided by 9. So it'd be 0.11. So there's only one sample point where they're both over budget. Okay, done with 17.
Why did you choose 2, 8, 3, 8, and 4, 8?
Which says stage 2 runs over budget if it takes 8 months to complete. The 8 is stage 2, taking 8 months.
So the second column is months.
Mm-hmm. So the thing that says in the third column where it says sample point, that's 2 and 6 months, 2 and 7 months, 2 and 8 months. Yeah.
Yeah, we're looking at 4.2 and 4.3.
Even though they're free.
I guess these second numbers.
Right.
Yeah, that's interesting. We did the whole problem without using 4.3.
We were just on the dog table.
Yeah. So we're going to redo the problem.
Well, you don't really need to look at table 4.3.
Yes, we do. We do need to look at 4.3.
It's supposed to be 4.3? It's
Hmm?
4.2 and 4.3.
4.2 and 4.3. So we just worked the problem where every event was equally likely.
Oh.
But now that I look at table 4.3, I see that each point isn't equally likely, and that makes my entire answer wrong, because I was supposed to consider both. So now we're going to try it one more time.
A, B, C, and D are all.
So A is correct the way it is. Okay, but B, we need the probability of what? Being over budget on the first stage. So the probability of 4, 6 plus the probability of 4, 7 plus the probability of 4, 8. That's what we're looking for. So now we're going to use 0.05 plus 0.10 plus 0.15, 0.30. And then our C answer is the same, because that was our data points. But our D response is the probability of 2, 8 plus the probability of 3, 8 plus the probability of 4, 8 0.05, 0.05, 0.15, giving me a 0.25. And then is the E answer the same? Being over budget on both would just be the probability of 4, 8, which would be a 0.15. Okay, now I take it into account both tables like I was supposed to. That better?
Yeah, hold on one second.
Mm-hmm. Want me to move up or down or?
So in order to get the like for example, say if they didn't have the
Here.
so say if they didn't have the 0.05 or 0.10 or
It didn't tell us what they were? So we didn't know what the probability of a
how would
particular
you
event?
get to that point?
If they don't tell us what it is, we can't do anything with it. So if it were equally probable, which is what I did first, then that's easy. But if they don't give us the probability, then it won't be a problem because we can't solve it. Okay.
23.
Next problem?
Yep.
2, 3.
You got it.
Certainly do hope the author gives us some difficult problems sometimes.
Oh, no kidding.
Yeah, I mean, really. 2, 3. Suppose we have 7 elements in our sample space. Right. The following probabilities exist. Okay.
Thanks.
Yeah, 169.
Oh,
Okay.
awesome.
Okay, so A. We want the probability of A.
Oh,
The following probabilities provide, let's say probability E, okay, so the probability of A would be the probability of E1 plus the probability of E4 plus the probability of E6. 0.05 plus 0.25 plus 0.1. 0.4. B. Nope, not B yet. We're still on A. The probability of B. Probability of B. Probability of E2. Probability of E4. Probability E7. Point 2, 0.25, 0.05, 0.50. The probability of C. Alright, probability E2, probability E3, probability E5, probability E7. 0.2, 0.2, 0.15, 0.05, 246, 0.6. So we want the probability, now we're on B. The probability of A union B. These are not mutually exclusive events.
so we need to find A union B first?
No,
No?
no. What we need to do is find on page 166. It says A probability of A union B is the probability of A plus the probability of B minus the probability of A intersection B. Okay, so what we need to do first is find the probability of A intersection B. Alright, so we come back at A and B. Oh, we can't come back up to A and B. We have to look in our page here. So the thing that A and B have in common is E4. So E4 is 0.25. 0.25. So the probability of, I didn't do that right, did I? Yeah, I did that right. Of A intersection B is going to be the probability of A, 0.4.
We're doing the intersection?
Where? B. B is union. We're on B. So I'm going to have the A, the probability of A, the probability of B, 0.5, minus the probability of A
Yeah.
intersection B.
Well, I know what you said, but why? I guess why?
Alright, so that'd be 9.9,
And you needed something.
0.65.
So, okay, there's one on the very top, the very end.
This
That
one?
should be a upside down view.
Yeah, that's not.
Okay.
Yeah, that looks like somebody's cooties or something up there, yeah. Minus probability A intersection B. Is that better? Alright. Yes. No. So we already did that guy. We calculated him. Now we got to get him. And with that, we can calculate the A union B. Okay, now the second part wants us to find the probability of A union Oh, we already did that. Okay, what you calculated the we didn't say what A union B were. So A union B is E1, E2, E4, E6, E7. So that was our we did that. It wanted to know that first, and union doesn't look like that. Union looks like that. Okay, that's better.
How'd you get 0.25 for A intersection B?
Okay, look at this set.
Yeah.
E4 is the only guy in both. So E4 being the only guy in both, I look and see the probability of E4 is 0.25. So this is the probability of E4 because he's the only guy that's in both. Okay.
Oh, okay.
Now, C is kind of redundant here, isn't it? C, because it wants to know A intersection B, which we already decided was E4, and the probability of A intersection B is the probability of E4. It would seem like I'd want to ask this one first, 0.25. All right. Are events A and C mutually exclusive?
Yes.
Yes, I agree. Delta, yes, because there's nothing that's in one that's in the other one. They may or may not be independent of each other. That's a different issue. E. Find the complement of B. All right, so the complement of B. Okay, so it's not B, so that means it's going to have E1 in it. It's going to have E3 in it. It's going to have E5 in it. It's going to have E6 in it. So that would be the complement of B. And then we want to know the probability of the complement of B. So that'd be the probability of E1 plus the probability of E3 plus the probability of E5 plus the probability of E6. .05, 0.2, 0.15, 0.10. The probability of the complement of B. 1, 2, 3, 4.40.
How are you coming up 0.4?
I don't know. I have trifocals on and I can't add.
Alright, I got you.
Is that better? Just checking the class. I honestly don't know how I could have possibly gotten 0.4 out of that. I think I'll go with age this time.
Okay.
I think that my Coke can's only I'm only a third done with my Coke, so it can't be that. All right, next problem.
29.
Oh, there are too many words in 29. How can we possibly do it? High school seniors, strong academic records, blah, blah. Because of the number of slots, stable, some colleges reject more early applicants. Suppose that a recent admission class received, okay, so I have 2851 applications. Now, the U.S. Coast Guard Academy is going to let 180 people in this year. How many applications are they going to get? 10,000. Totally amazing. Okay, so of this group, it admitted 1,033 early. So did any of you guys put in for college for early decision? No, neither did I. And it rejected 854 rejected. And deferred 964 deferred. Oh, I heard a really cool thing on the news yesterday. And the issue is we're going to allow females into our combat positions. And the issue is that if in fact that's what we're going to do, shouldn't we also be issuing them draft numbers? So
Equal rights.
equal rights. You know, if you want equal rights, you have to take equal responsibilities, right? Anyway, needless to say that there was silence in the room because no one wants to take on that issue.
I think they should.
There you go.
You want equal rights, guys? Go for it.
To get deployed?
Yeah.
I don't know that I say you take care of my children. And I work in a school. Want to send me over there.
All right, somebody grab that bag of worms and run with it.
I went to combat with
I think it
Three
all
other
should just
women.
be, you choose to do it. I would say that.
Yeah, I can imagine.
There you go.
Like,
There'll be plenty of equal rights when the bombs are dropping here. Don't worry about it.
Bomb drop shoes.
In the past, the school has admitted 18% of the deferred. 18% of deferred. Counting the students admitted early and the students admitted during regular admission process, the total class size 2375 total. Let ERD represents the events that a student who applied early is admitted, rejected outright, or deferred pool. Okay. So I think we know what we're talking about here. Maybe. So A, find the probability of E, the probability of R, and the probability of D. All right, so we have 1033 are early, rejected 854, deferred 964. Now the issue is, what are we dividing by?
Total, isn't it?
Are we dividing by the total class or the total applicants? The probability of early, we're probably doing it from the applicants. 2851, 2851, 2851. This time we don't have to add, so it should be better, right? .36. 0.30. .33. We'll make it 0.34 and then it'll add to 1. Okay, we'll round this guy up. And that's a total of 1.00, so that looks good. Are events E and D mutually exclusive? Yes. If you're admitted, you can't be declined, right? So part B, yes. The probability of early admission intersection telling to go away is 0. Right? So if I was wait a minute, early admission deferred. No, early admission deferred. If you're early admission or you're deferred, then the intersection of those two events has to be 0. You had to be 1. If you're 1, you can't be the other. Okay. For the 237 students who were admitted, what is the probability that a randomly selected student was accepted during early admission? Okay, so that would be 1033 divided by 2375. We'll go with 0.43. Suppose a student applies for early admission. What is the probability that the student will be admitted for early admission or be deferred and later admitted during the normal process? Okay, so So there, and 18% of the deferred guys, 964, divided by, suppose a student applies, what is the probability that the student will be admitted, early admission, or deferred? Okay, so that'd be divided by the total applicants. 2, 8, 5, 1. Okay. 1033 plus 18% of 964 divided by 2851, and that would be 0.42. Yes? Yes, no, maybe. Next problem. 35. According to the Ameriprise Financial Money Cross-Generation Study, 9 out of 10 parents with adult children have helped their children with some type of financial assistance, ranging from college, car, rent, utilities, credit card, down payment on a house. Okay. 9 of 10, 20 to 35 age. I don't think we're going to need the age. That might just be something. So I fall into that category. I have 4 children in that age group, and currently I'm helping all 4 of them somehow. So my son's living in my house in Georgia. My daughter's credit card still has my name on it because she can't have credit without my name on it. They all add up, right?
You're too nice.
Yeah, I know. You do what you do for
Want some more
family.
kids?
Why, you guys want to apply?
Why
Yeah.
not?
Sarah, I don't, well, yeah, I have a daughter that graduated from the Coast Guard Academy that's currently a GS-14. I don't think I'm doing much for her right now, but she has 2 little girls and we send her clothes all the time, so I'm doing stuff for her too, right? Because mommy can't shop. So, and they're at Fort Meade, Maryland. Well, what are we doing here? The following table with sample data consistent with this study shows the number of times parents have given their adult children financial assistance to buy a car and to pay rent. Buy a car, yes, no. Pay rent, yes, no. Okay. I see it. I see the table. A. Develop a joint probability table and use it to answer the remaining questions. Okay. So we're going to go and have buy car. Yes. No. And we're going to have a pay rent. Yes. No. And we want a joint probability. Okay, so so we need a total number. So what's 56 plus 52 plus It is 14 plus 78. Does it say that someplace that there's 200 of them?
Did it?
Oh, you just did it. So that's 200. So we're going to go 56 divided by 200 and 14 divided by
You mean plus
200.
78, right?
Yeah.
Oh.
And 52 divided by 200 and 78 divided by 200. Okay, now we're going to do those things. 56 divided by 200. 0.28. 52 divided by 200. 0.26. 14 divided by 200. I bet you it's 0. I bet you it's 7. What do you think? 0.07. And 78 divided by 200. 0.39. And if we add them all together, we should get 1, right? So 0.28 plus 0.26 plus 0.07
Oh, that's 70.
plus 0.39, boom, 1. Okay. So we got 1. All those things are right. All right, so now we're ready to part B. Using marginal probabilities. Using the marginal probabilities for buying a car and paying rent, are parents more likely to assist their adult child with buying a car or with paying rent? What is your interpretation of this? Yes, they're more likely to pay for the car. Okay. My interpretation of that is that parents are really cheap. A car is a one-time thing, rent is forever. No, is that something like that? C. If parents provided financial assistance to buy a car, what is the probability that the parents assist with paying rent? So that would be car and rent, 0.28. D. If parents did not provide financial assistance in buying a car, what is the probability that they did pay rent? 0.07. That guy right there. If financial assistance to buy a car is financial assistance to buy a car independent of financial assistance to pay rent? And the answer is no, they're not independent. Wait a minute. They're not mutually independent. They're not mutually exclusive, but are they independent? Independent events. All right, so independent events, E. The probability of A, B, is the probability of A. So if that's true, the probability of A given B is not A. If that's true, then the events are independent. Okay, so the probability that A's occurred, okay, the probability that buying the car has occurred, what is the probability of paying the rent? The probability of paying the rent has occurred. What's the probability of paying for the car? Yes, it looks like these guys are in fact independent.
How does A and B equal A?
The probability of, okay, that's a good question. The probability of buying the car is 0.54. The probability of paying the rent is 0.35. Okay, so is the probability, given that I've already bought the car, what's the probability of paying the rent? Given that I already bought the car, the probability of having the rent paid is 0.28. But the probability of having the car is 0.52, 0.54. That's not equal. Not equal. Therefore, my events are not independent. Therefore, events not independent. All right, like that better? F. What is the probability that the parents provide financial assistance for their adult children by either helping buying a car or rent? Okay, so we want the probability of car union rent. Okay, so that's what we're looking for, car union rent. So that's going to be the probability of buying the car plus the probability of paying the rent minus the probability of the car intersection rent. Alright, so probability of buying the car, 0.54. Probability of paying the rent, 0.35. Probability of doing both rent and car, is it 0.28? 0.28. Now, seeing that I did so well on this last time, this time I will use my calculator. Point 0.61. 0.61. Next problem. 40. How many more problems are there? This is this
4, 5.
5 more?
No, 4.
4 more?
41, 47, 53, 59.
And then 65.
Yeah, whatever you say.
Nope.
You're in the wrong
Oh,
one.
sorry. We don't have 65. We have that on Thursday. I'll be here. Sorry.
You have to use 65 then.
Okay, so number 41. A consulting firm submitted a bid. Okay. We're